So let me explain how to find maxima or minima of a function subjected to given constraint. Let's assume that you are given with some function like this, f of x comma y, that equal to maybe that is x square plus y square minus 2x plus 3. So this is the function, and the question is to find maximum and minimum of f of x subjected to the constraint. So phi 1 of x equal to let's assume they gave 2x minus y plus 3 equal to 0. So there is only one constraint they gave us. Subjected to this constraint, we need to find maxima or minima of the function. So geometrically what they are asking is, let's assume that you have this function like this. Okay, why? Because it is a function on 3 variable, right? So the domain, I'm going to take it here. So assume that one is x-axis, another one is y-axis, and this is z-axis. Okay, so now you may have some function like this. The graph of the function may be given by some surface like this. All right. And here what we are doing is the constraint function, the constraint, it is a line somewhere here. I'm just randomly drawing it. Okay, it is a line on the xy plane. Now corresponding to this line on the graph, we may find some curve like this. So corresponding to this line, we may find something like this. Okay, and these endpoints are related to the endpoints here. Now what is our interest is, we need to know what is the maximum or minimum of this function, the constraint function. It means you are not considering the domain is all. You're actually considering the restricted domain, and the restricted domain is nothing but 2x minus y plus 3 equal to 0. Okay, and this problem can be done in two ways. One, using the concept of Lagrange multipliers, and another by direct substitution. Alright, so let me explain these two methods. So the first one, let me go by direct substitution. Okay, so I'm going for the direct substitution to solve this problem. So now what shall we do? So first you take the constraint. Our domain is restricted. What is our domain? So that is what constraint. So the constraint is nothing but 2x minus y plus 3 equal to 0. Okay, it means from this I can write what is y actually. Y is nothing but 2x plus 3. Okay, so y is 2x plus 3. So this is what the constraint. Now let me see what is the function if I restrict the domain to y equal to 2x plus 3. That is f of x comma. Now in place of y, I'm going to substitute this 2x plus 3. Okay, so in that case our function is x square plus, what is our function here? X square plus y square. Y square is nothing but 2x plus 3 whole square. Okay, minus 2x plus 3. So I simply substituted y, that is 2x plus 3. Okay, now this implies, now f totally became a function of x alone. So now f of x equal to this one. Maybe you can do some simplification. After some simplification, I hope you can find it is 4x square plus x square, finally 5x square. Okay, let me just write it as f. So now finally after substituting the constraint function, now f equal to 5x square plus, and here you'll have 6 into 2, 12, 12 minus 2, 10, that is plus 10x, and here you have 9 plus 3, 12, plus 12. So this is the function after substituting the constraint. It means when you substitute this line in the function, so the restricted graph is a parabola which is given here, which is given by the equation 5x square plus 10x plus 2. Okay, now I want to see where this parabola is taking maximum or minimum. So what do you do now to find maximum or minimum? We will simply take the first derivative of f of x and we equate it to 0. Alright, so what is f dash of x here? So f dash of x is nothing but, so this implies that is 10x, yeah, and plus 10 plus 0 equal to 0. Okay, because it's the first derivative is 10x plus 10, okay, plus 0. So this implies, now this tells me that x plus 1 equal to 0. Now this says x must be equal to minus 1. So yeah, whenever you have a parabola, no, so the parabola will have only either one minima or one maxima. Okay, that's why you got only 1 point here. All right. So now at x equal to minus 1, so x equal to minus 1 is the critical point of the function. So let me write x equal to minus 1 is a critical point of f subjected to phi 1 equal to 0. Okay, subjected to the constraint, our critical point is minus 1. All right, so let me know whether f takes maxima or minima at that point. So here, whenever it is constrained optimization, definitely either it takes maxima or minima. You can simply do one thing. You can substitute what is f of minus 1, okay, in the function itself. Here, now we are taking f equal to what? Here f is actually equal to 5x square plus 10x plus 12. This is what, right? And it is an upward parabola. So it is very clear that it has minimum at x equal to minus 1. But however, let us get it confirmed. So what is f of minus 1 here? This is 5 minus 10 plus 12. Right? So this is what 7. Alright. Now, to know whether it is maxima or minima, you just take one point in the neighborhood of minus 1. Okay, suppose if I take 0, maybe it is far, but fine. F of 0 is actually 12. So this 7 is less than 12. Alright. So not only that, you take very close point. Maybe you can take minus 0.09. If you substitute f of 0.9, whatever value you obtain, you can find that is greater than 7. This is also greater than 7. So it is very clear that it has minimum at that point. Okay, this is one way of confirming whether it is minimum or maxima. Or you can do one thing, you can go for a second derivative test. What is the second derivative test here? So take the second derivative of f, that is actually 10 itself, because the first derivative is 10x plus 10, so the second derivative is 10, and which is positive. So therefore it is very clear that f has minimum at x equal to minus 1. All right, so now what is the minimum of f subjected to the given constraint is, so minimum of f of x comma y subjected to the constraint phi 1 of x comma y equal to 0 is, what is the minimum value? That is f of minus 1 comma, if x is minus 1, what must be y? y actually, okay, minus 2 plus 3, that is 1. Y must be 1. So that equal to, after substitution, what do we get here? That is 7. Okay. So this says something. When you restrict your domain to a line, the function is having only minimum. There is no maximum. That's it. It is not having maximum. It has only minimum. All right. Okay. Let me show you this graphically also. So let me take the function here. So that is x square plus y square. And what is it we have taken? Minus 2x plus 3. All right. Minus 2x plus 3. All right. So now you see this is a parabola. All right. I hope you can see that parabola. Yeah. Now let me make it big. So this is the parabola you have. Now what we are doing, we are simply taking a line. What is that line? 2x plus y minus, what is it I have taken? 2x minus y plus 3. All right. So 2x minus y plus 3. Okay. So now what you can see in this picture, is the intersection of the parabola with the plane actually, but we are not taking the entire plane. So we supposed to get a line here. Let me do one thing. Let me simply draw a line here like this. I'm not getting it. Yeah. So this is the line you have. When you intersect the line here, so after intersection, what do you get? You will get a parabola like this. Okay, that will have only minimum. You can't find maximum for it. Okay. So I hope you understand geometrically also what happens. So if you restrict your domain to a line, on the image of that line is going to be a parabola, upward parabola, and it is going to have only minimum. And if you inquire that where is that minimum occurs, we know it occurs at minus 1. Okay. All right. Okay then. Now this is what, by using direct substitution, like you can find y in terms of x or x in terms of y, substitute in the function, and then you find maxima or minimum of the function directly. Okay, so let us solve the same problem with the help of Lagrange multipliers. So in Lagrange multipliers, the problem is to find or is to maximize or minimize this function subjected to the constraint, maybe phi 1 equal to 0 or phi 2 equal to 0. You can have more than one constraint also. Okay, so let me talk about one constraint first. Later we will think about the more constraints. So here the basic idea here is we need to see the level curves of the function. Okay, so level curves, it means you equate it to a constant, and on an xy plane, you draw the level curves. The level curves may be circles or maybe rectangles. It depends on the graph. Okay, so you draw the level curves of the function. So after drawing the level curves, and you draw what is the given the constraint. Maybe let me assume that the given constraint is just this a kind of a box like this, a rhombus. Okay, this is the given constraint. On this constraint, I would like to find maxima or minima of the function. So maxima or minima definitely is going to attain at this point. One point is this, okay, and another point is this, other one is this, another other one is this. You may ask me, sir, how you are telling? Because I have to just see where the given constraint touches the level curves, where the constraint curve is tangent to the level curves. If the constraint curve is tangent to a level curve, then definitely there you are going to have either maxima or minima. So if you see the tangency, this is where you can actually see. All right. Maybe if the things are not so clear, let me explain with an example. So let me take our function to be f of x comma y, that is x square plus y square. Okay, and you may take it as z is equal to x square plus y square. And what is the picture for this function? You can see that is a upward paraboloid. All right, so this is an upward paraboloid. Now this paraboloid I'd like to intersect with a curve. Okay, so when I intersect with a curve, maybe let me intersect with some ellipse. So I would like to intersect this with an ellipse that is given by x square by 4 plus y square by 9 equal to 1. So this is the constraint. So now what is the maxima or minima of this function subjected to this constraint? It means it is same as finding that you take the domain of the function. Okay, so you take the axis. You can name them as x-axis, y-axis and z-axis. All right, now you draw the ellipse. This is 4 on x-axis. I need to take 2 here. On y-axis maybe 3 here. Now you draw an ellipse. Okay, so this is the ellipse. Now what do? You're going to intersect this ellipse with this paraboloid. Okay, so when you intersect, what is the exact intersection? Can you see? It's a kind of Aravanki shape. I don't know whether you know the Aravanki or not. that is one of the ornaments you use it to wear for to hands, right? Yeah. I hope you can see it on the screen how Aravanki looks like, right? So I mean, when you intersect this paraboloid with an ellipse, this is the kind of shape you're going to get, and it's actually not straight. Okay, if you keep it straight, you can see that the minimum is occurring here, whereas the maximums are occurring here. Okay, so this is the point where the minimum occurs and this is the point where the maximum occurs. So let me use just some different colors to show it. All right, so the maximum occurs here. All right, whereas the minimum points are actually here. This is where the minimum occurs. So let me solve this problem. So now let me see geometrically first. So geometrically, in terms of level curves, if I see, first you print the level curves of this. I think I don't have something to neatly write the circles here. No, I am very bad at drawing. Anyway, let me draw it with a dotted line, so somewhat looks like circles. Okay, so these are actually level curves of the given function. Level curves, I mean f of x comma y equal to k. It means x square plus y square equal to k. What it means? They are nothing but circles. Alright. So these are the circles here. So level curves are nothing but circles. Now let us draw what is the given constraint. So the given constraint is an ellipse, which is on x-axis its length is 2, on y-axis its length is 3, maybe here. Okay. Now if you observe that the level curve is tangent to the given constraint at this point and at this point. So here this point, either it can be a point of minima or maxima, and similarly the rest of the points, they can be minima or maxima, these 2 points. Now if I compare with the graph, these red color points are on the y-axis, right? So these are the red color points here. So these are the red color points, and let me tell you what are these level curves actually. So when k equal to 0, you will just get a dot, all right, and the second dotted circle is k equal to 1, and the third dotted circle is k equal to 2, and the fourth dotted circle is k equal to 3. Okay, I mean if I not k equal to 3, this is actually, let me, k equal to 9, not 3. Because if k equal to 9, then only I will get a circle with radius 3. So this is k equal to 1, and this is at 4, and this is at 9. That's it. And whereas this is at some, let me assume, next 16. Yeah. Now you see, now among this case, which least k which touches the graph, touches this ellipse. So the least k is here. That is what, k equal to 4. And the highest k is k equal to 9. That's it. Okay. So the corresponding circle here at k equal to 9 will be here. This is the corresponding circle. Okay. And the least circle is here actually. It's a kind of something like this you get. Okay. But anyway, so here all I wanted to say is, at the point of maxima or minima, these two constraints and level curves are parallel to each other. It means their normal vectors are also parallel to each other, and you can find the normal vectors by using the gradient definition. So the gradient of f will give you normal vector to the level curve, and similarly let me assume this constraint is phi, and gradient of phi will give you the normal vector to the constraint. And we are saying these two vectors are parallel. If they are parallel, one must be a constant multiple of other. So it means at a point of maxima or minima, these two gradient curves are equal. It means what do we mean by gradient? fxi plus fyj must be equal to lambda into phi xi plus lambda into phi yj. These two are equal. It means we are saying that fx minus lambda into phi x into I plus this fy minus lambda into phi y into j, this must be equal to 0. It means what? It means that fx minus lambda phi x must be equal to 0, and fy minus lambda phi y must be equal to 0. Okay, so without any loss, this lambda is a constant, right? So I am taking this to be minus lambda. So if I take minus here, then I get minus here and minus here, so that plus and plus and plus. It is nice to see in this form. Now, so at these points, what happens? These two partial derivatives are becoming 0. Now what Lagrange has done is, so to find maxima or minima of a function subjected to the given constraint, he has written a new function, that is f of x comma y, and which is given by f of x comma y plus lambda into phi of x comma y. That's it. So if you want to find the points where this f takes maxima or minima subject to the given constraint, you find partial derivatives of this capital F and equate it to 0, okay, like this, and you find the points where these two guys are 0. So that gives you the points where small f takes maxima or minima subjected to this phi. Okay, so whatever constants you are multiplying, these are what we call Lagrange multipliers, and this is what actually method of Lagrange multipliers. Okay, so in the Lagrange multipliers, what do you do? Whenever you are given with some function f, so you will be asked to maximize or minimize f of x1, x2 and so on xn, okay, subjected to the constraints, maybe phi 1 of x1, x2 and so on xn equal to 0 and phi 2 of the same thing equal to 0. So you may be given with k functions. Okay, if you have k functions, we will write k lambdas. So then you construct a new function, that is consider capital F of x1, x2 and so on xn, and along with that lambda 1, lambda 2. If you are only two constraints, 2 lambdas. If you have 3 constraints, 3 lambdas. Okay, and this new function is nothing but that is f plus lambda into phi 1 plus lambda 2 into phi 2. Okay, so now all that you need to do is find critical points of capital F. So find critical points of capital F, and it is sure that at these critical points this function f either has maxima or minima subjected to the constraint phi 1 equal to 0 and phi 2 equal to 0. Do you understand? So this is what we do in the method of Lagrange multipliers. So first you need to identify which function you need to maximize or minimize, and you need to know what are the constraints. Once if you know the function and the constraints, then you can construct a new function like this and just find the critical points. Okay, so let us do one thing. Let us try to solve the previous problem using Lagrange multipliers. So what is the previous problem? Let me pick up. Okay, so this is the problem, right? So here it is very clear what is the function we need to maximize and what is the constraint. So now let us use the Lagrange multipliers method to solve it. Okay, so now let us consider capital F of x comma y. You may call this as a Lagrange's function. So that is small f of x comma y plus lambda into phi of x comma y. Yeah, I must write x comma y here. It is not just phi 1 of x. Okay, so now that is f of x comma y, that equal to, what is f of x comma y here? X square plus y square minus 2x plus 3. Okay, plus lambda into, this is 2x minus y plus 3. So we wrote this function f of x comma y. Now what shall we do? Let us equate the partial derivatives fx equal to 0. Now this implies 2x minus 2 plus lambda into 2 equal to 0. Now this implies, maybe you can write it like this, x minus 1 plus lambda equal to 0. Alright, keep it side. And similarly, take the partial derivative with respect to y and equate it to 0. So with respect to y, what is its partial derivative? This is 2y, okay, plus lambda into minus 1 equal to 0. So from this it says, what it says, y equal to lambda by 2. So y equal to lambda by 2, and the first equation also telling me that x equal to 1 minus lambda. So we got x and y in terms of lambda. Now we have a constraint. No, what is that constraint? The constraint is phi of x comma y equal to 0, that is given by 2x minus y plus 3 equal to 0. See, our interest is this. We would like to find maxima or minima subjected to this constraint. It means our x comma y has to satisfy this equation. It means whatever you get here, x comma y, you substitute it here, and accordingly you find lambda. So if I substitute this, so 2 into, you get 1 minus lambda minus y, that is lambda by 2, plus 3 equal to 0. Now this implies, after simplification, I hope you can see, this is 2 plus 3, 5, minus 2 lambda and minus lambda by 2 equal to 0. Now this implies, now this is minus 5 lambda, yeah, and send it to the other side, that becomes plus 5 lambda equal to 10. Yeah. So this implies, what is lambda? Lambda must be equal to 2. That's it. So if lambda 2, therefore what is x? So x equal to 1 minus 2, that is minus 1. And how about y? Y equal to lambda by 2, that is 2 by 2, and which is 1. I hope in the previous problem you must have remembered. So the critical point x comma y, there we got minus 1 comma 1. Do you remember? Okay, let me show you that. You see, which is here. At minus 1 comma 1, the function is having minimum subjected to that constraint. So the whatever critical point we got here is this minus 1 comma 1. Now you just see one thing, what is f of minus 1 comma 1? What is it? And the value is going to be 7. And we can see that this f of minus 1 comma 1 is always less than or equal to f of x comma y. Okay, to see that, you do one thing, you take x equal to some value, y equal to some value which is near to minus 1 comma 1, and you see, you can identify that this is maximum. Therefore f has minimum at minus 1 comma 1, subjected to given constraint. I hope you understand. Okay, let me solve that Aravanki problem, this Aravanki problem. So what is it I have taken here? So f of x comma y, that I have taken x square plus y square. Yeah. And what is the constraint? So the constraint is nothing but, so the constraint is x square by a square, sorry, x square by 9 plus y square by 16 equal to 1. All right. Now let us write the solution. So the question is to maximize or minimize this function subjected to this constraint. Okay, so that is the question. So now let us use the method of Lagrange multipliers. So this is what I am using, Lagrange multipliers. Okay, so I need to construct a new function, capital F of x comma y, and that equal to small f of x comma y plus lambda into phi of x comma y. Okay, so this implies what is f of x comma y? So this will be x square plus y square plus lambda into x square by 9 plus y square by 16 minus 1. So what shall we do? Let us take fx equated to 0. This implies 2x plus 2 lambda x, okay, by 9 equal to 0. All right. Now this implies you have two options. Okay, x into 1 plus lambda by 9 equal to 0. Okay, similarly you take fy and equate it to 0. This implies 2y plus 2 lambda y by 9 equal to 0. This implies y into 1 plus lambda by 9 equal to 0. So here there are two situations. One, so this tells me that, so fx equal to 0, so this tells me that either x equal to 0 or x is not equal to 0. X is not equal to 0, it means 1 plus lambda by 9 equal to 0. That's what. Okay, if x equal to 0, let me see. If x equal to 0, then it has to satisfy the constraint, right? What is it? X square by 9 plus y square by 16 equal to 1. Now this implies if I substitute x equal to 0 here, y square by 16 equal to 1. It means y square equal to 16. Now this implies y equal to plus or minus 4. Okay, so therefore it says something, when x is 0, y can be plus or minus 4. So this is one critical point. All right. And second case, x is not equal to 0. So if x is not equal to 0, then definitely 1 plus lambda by 9 must be equal to 0. But if I equate this lambda to 0, I don't get anything. All right. So now let me see fy equal to 0. This also tells me two possibilities, y equal to 0 or y is not equal to 0. Suppose if y equal to 0 and it has to satisfy this equation, and this implies that x square by 9 equal to 1, and this implies that x equal to plus or minus 3. All right. Now what are the critical points? Plus or minus 3 comma 0. That's it. So now the only critical points we got here is either it is 0 comma plus or minus 4 or plus or minus 3 comma 0. Now let me see what is f of 0 comma plus or minus 4. So that is what actually x square plus y square, right? So that is 0 square plus or minus 4 whole square, which is actually 16. Okay, and similarly f of plus or minus 3 comma 0, which is plus or minus 3 whole square plus 0 square, which is 9. Now it says that it is maximum and this is the minimum. Okay, now in the Aravanki, the Aravanki that is of this shape. Okay, and this point in the domain, the corresponding point in the domain, this point is actually 0 comma 4 minus 4, and this is 0 comma plus 4. And if you see what is this point is 0, -4 and 17. Okay, and this point is nothing but 0 plus 4, 17. Oh, sorry, not 17, sorry, 16. So this is 16. Okay, and how about this guy, these two guys? Here it has minimum, no? And you know what is the point of minimum here? So the point of minimum is, one point is -3 comma 0 comma 9 and another point is +3 comma 0 comma 9. So those are the points. Okay, so this is how, using the method of Lagrange multipliers, you can find maxima or minima of a given function. So this is the constrained optimization when you are given equalities. Okay,